Okay, welcome. This is the first part of linear momentum that we'll talk about here. Um, linear momentum is defined as a product of an object's mass and its velocity. So we have two things coming into play here. If an object has mass and it's moving, then it has momentum. It's sort of like the momentum that we talk about in real life, right? The football team had momentum. Well, it doesn't really mean that they had mass and they were moving. What it meant is they were going forward with this thing called momentum. Linear just means a straight line. So we're just going to be looking at momentum in a straight line. We're not going to do any curves or two-dimensional thing. So the formula for that is we use a P for momentum. Who knows why they chose P for momentum? Maybe translated into another language it means something. But we simply take P, which is boldface, which means it's a vector, equals the mass, which is a scalar, times the velocity vector. So this is another formula. You'll find that right on your formula sheet. The units for momentum is kilogram meters per second. Now there's no special name for this, so we just, every time we talk about momentum, we talk about kilogram meters per second. But this is the big hint that when you're doing your calculations for momentum, be sure you're in kilograms, be sure you're in meters and seconds. Okay, so let's try a very simple example. Let's calculate the momentum of me on a rolling chair with a mass of 82 kilograms and a speed of 3.5 meters per second. So we simply take this formula, P equals mv, and as simple as it is, we put the mass in place in kilograms, 3.5 meters per second is the velocity. Do that product, and it's 287 kilogram meters per second. Okay, so maybe that's to help you get a reference. You can just imagine me in a rolling chair going 3.5 meters per second, which is actually pretty fast. But you get an idea of what momentum is all about. Okay, so with momentum, bad. Dang it. So with momentum, force is a cause of the momentum. So either an object that is at rest, a force put onto it will give it momentum, or if it has momentum, a force will take the momentum away. In actuality, Newton's second law was actually written in terms of momentum. If you remember, sigma F equals ma, well, sigma F equals the change of momentum over t. Right? And we can show how that works, where momentum is mass times the change in velocity, and the change of velocity over time is acceleration. And he actually defined his second law using momentum. The net force of an object is equal to the rate of change, which is the derivative, of its linear momentum in an inertial reference frame. So those are the actual words of Newton, or at least translated, or I guess not translated because he was English. And those are the actual words of Newton. So we can use this also to define the force involved in terms of momentum. So our first example is to calculate the force exerted on a baseball with a mass of 145 grams that goes 90 miles an hour to 0 in 0.02 seconds. So this is like a ball being pitched at 90 miles an hour, and then the catcher catching it in 0.02 seconds, very quickly. So to do this, we of course have to change our mass from grams to kilograms. It's very important. And because I give it to you in miles per hour, then we actually have to change that to meters per second, and I'm sure you remember how to do that. So that comes out to 40 meters per second. So now we have the mass and we have the velocity in the correct terms, so we can get the momentum. So we can use Newton's second law in terms of momentum. The change of momentum, we're going from 40 meters per second to 0. So we can write that as V minus VO, because that's the change. And then put the mass in. So it goes in something like this. 0.145 times 0 minus 40. That's the way it is, because 0 is the final velocity, 40 meters per second is the initial velocity, and then we put the time in. And that comes out to 290 newtons, and that you should know is a pretty large force. You can just imagine a catcher catching a 90 mile an hour ball and the force exerted on that. So how much force or how much time does the pitcher exert a force on of 15 newtons in order to throw the baseball 90 miles an hour? So now we're just going to use this same formula, but now we're going to do it in terms of time. We're not going to use, the baseball and I mean, we are going to use the baseball mass and everything. We're just going to rearrange this so that time is the change in momentum over the sum of all forces, which were given as 15. And so very simply, we put the mass in, a change in velocity over 15, and then we get 0.39 seconds. So less than a second, the pitcher is exerting this 15 newtons to get it up to 90 miles an hour, and then in 0.02 seconds, the catcher catches the ball. Okay, so ponder this. A heavy object and a light object have the same kinetic energy. Now remember back from when we talked about kinetic energy a few days ago. Which, if any, has the higher momentum? So here's a way you could do that. Assume that a heavy object is 4 kilograms, going 2 meters per second. We calculate that kinetic energy, 1/2 mv squared, to 8 joules. We then take a lighter object, lighter than 4 kilograms, and we're going to calculate the speed from that, because now we know if they have the same kinetic energy. So if the light object is 1 kilogram and the kinetic energy is 8 joules, then it's going 4 meters per second. You can show that math very simply, right? So, therefore, the heavy object's momentum is mass times velocity for 8, and the light object's momentum is 1 times 4, or 4 kilogram meters per second. So the two objects have the same energy but different momenta. Maybe that can twist your mind a little bit. All right, so now the conservation of momentum. Just like energy, momentum is conserved. So the total momentum of an isolated system is conserved. The word isolated means that there are no forces coming in or out, or no mass coming in or out. So it's all conserved with all those things. So we say that the momentum before is equal to the momentum after. And there's a different way we're going to subscript that. You'll see in a second. Let's take these two balls. Here's the beginning picture, right? We have this ball 1 has a, so we subscript it mass 1 and is going velocity 1. It happens to be going to the right. And we have mass 2 and velocity 2 going towards it, the opposite direction, right? And so we can actually calculate the before picture. They hit, and now they're going the opposite direction. And so we now have mass 1, which hasn't changed, times velocity prime 1. So that means that little prime symbol up there means that it's a different velocity than the initial velocity. Same with the velocity 2. It's just a different one from that. The masses haven't changed. So we write this as the momentum, the total sum, m1 v1, that would be the momentum of the first object, plus the momentum of the second object, is equal to, afterwards, the momentum of the first object with the new velocity, plus the momentum of the velocity in the second object. But be careful because they are vectors. So we have to take the v's in consideration. They're going opposite here, so we do a plus and minus on that, and then we have a minus and plus going on there. So, but just watch out for the directions, and we'll do an example problem to show how that works. Okay, we're going to do an example. Here we have one train sitting on the track. That's B right there, has a mass of 10,000 kilograms. So its velocity is 0 because it's sitting there. The other train, this A train, has a mass of 15,000 kilograms, and it is moving at 24 meters per second to the right. When they collide, they couple together, which means they connect together and then they travel off together. So the question is, what velocity do they move with? Okay, so we start out with the conservation of momentum, which says that the initial momentum of the system is everything in this box there, is equal to the final momentum. So that means the sum of these two objects with their momentum each will equal the final momentum. And so we'll look at this first as we take the mass of A times the velocity of A, that would be the momentum of object A, and mass of B times the velocity of B, that is that one initially. So that's all at the beginning, so we just simply add those two together. They both have momentum. The one afterwards, now we have the combined mass A and mass B. So we add those two masses together and we multiply it by the final. Down here it's VF, but up in the picture it says V prime. So the prime, or the little asterisk after the V, just means it's going to be a different velocity than any of the other two given. I think it's clear if I subscript it with an F to mean that's the final velocity. Okay, so next we're just going to take the numbers that are given and plug in. So we have 10,000 times 0. That would be, I got that backwards. Anyway, 10,000 times 0 would be the mass of car B times its velocity, which is 0. So it does not have any momentum because it's sitting there. And then all the momentum comes from the 15,000 times 24. And that's going to be equal to the sum of the two train cars and then velocity. So to calculate this, we're going to take 15,000 times 24, and then we're going to divide it by 25,000. Go ahead and do that calculation and pause the video. So you should have found that the final velocity is 14.4 meters per second. Pretty straightforward. The whole key there is the conservation of momentum that we just learned on previous screens. Okay, let's try another one. So here we have a train car. I don't know why momentum has to do with train cars, but we have a train car that is 12,500 and it moves at 18 meters per second. This one's moving to the left. And a 5,750 kilogram load is dropped into the car. Oh, and so what we're going to do is we're going to find out what is the speed of the rail car and the load. All right, so we attack this exactly the same way. First line is going to be the conservation of momentum. The initial momentum is equal to the final momentum. Well, the initial momentum will be the car moving to the left. We do not count the momentum of the falling object there because it's perpendicular to the momentum of the car. So we have the momentum of the mass of the train times the velocity of the train equal to the sum of the two masses and then the final velocity. So we put in the numbers. 12,500 times 18 is going to be equal to 12,500 plus 5,750 times V. So go ahead and do that math and pause the video. So then you should have found that the final velocity is 12.3 meters per second. Right, so that's the first type of collision is when they come together and they're in the same direction now, perpendicular, but we don't consider any momentum of this because it's not going to add or subtract to the sideways momentum. Okay, let's do one more example. So we have this 15-gram bullet that is shot from this gun right here and becomes embedded in a 1.1 kilogram block of wood that's on the floor. If the block and if the coefficient of friction is 0.25 and the impact drives the block a distance of 9.5 meters before it stops, like that, what was the muzzle velocity of the bullet? So the muzzle velocity will be the speed that the bullet leaves the muzzle, and we're assuming it doesn't lose any speed from here to there. Okay, so we can do that by using two things. So we're first going to figure out how much, what the velocity of the block and bullet was as soon as the bullet became embedded. So we're going to use the work energy theorem on that we learned earlier in the last unit. So, and that says that the work that it has at the beginning is going to be transferred into the, well, actually the other way around. The kinetic energy it has at the beginning is going to be transferred through work, and that will stop it there. So we're going to use the force of friction times the distance that it travels, and that's going to take all of this kinetic energy away that it has before it starts sliding. So we're not going to deal with this individual bullet yet. We'll do that in a second. So the formula for that is going to be mu mg, and that's going to be of the mass of the bullet and the block times the distance that it travels, and that's going to be equal to the kinetic energy it has when it starts sliding, which is 1/2 the mass of the bullet and the block times the velocity of the bullet and the block squared. Okay, so we have the work and the energy. Now you'll notice that the mass of the bullet and block is on both sides as a factor, so we could actually cancel those out right now. But I'm going to leave them in because most students would just leave them in, and they'll put the 0.25 and the mass of the combined mass of the block. So the mass is 1.15. I didn't even put it in correctly because it cancels out. Oh well, 9.8 and times 9.5 the distance, and then that's equal to 1/2 of the mass and then velocity squared. So my suggestion is to just leave the masses out on both sides because they cancel, and then it's just 0.25 times 9.8 times 9.5, and then we're going to cancel that out, divide it by 1/2, and then square root. So pause it and do the math on that. You then get 6.8 meters per second. Now that's not the question. That is not the velocity of the bullet, because that's the velocity of the block and the bullet as soon as it starts sliding. So what we're going to do now is we're going to look at the conservation of energy before and after the collision of these two. So before, the momentum before comes from the bullet and the block, of course is not moving, and the bullet this is the velocity we'll be trying to get right there, the v, little b. So now that's going to be equal to the momentum afterwards, which is the sum of the two momenta, and times the velocity of the two, which we're going to use the 6.8 down there. Okay, so plug in the numbers. There's the mass of the bullet. The velocity of the bullet is what we're looking for. This all changes to 0. We're going to add those two together and make sure you add them together properly like I did above, and times 6.8. So to calculate this, do the right side, and then you can divide it by 0.015. Pause the video, do your calculations, and it comes out to 505 meters per second. So that's those are 3 examples of linear momentum. You should be able to just calculate simply given mass and velocity of objects, calculate the momentum, or use the conservation of momentum in problems, and then of course it gets a little bit stranger when we deal with energy. We'll do a lot more examples. Okay, so if you have any questions, contact me in the usual way. Thanks for watching.